Hi everyone, I'm here with you in avatar form because I have an appointment. Luckily, all we have to do today is focus on the third and final application of the dot product. That would be projections. And whatever amount of time we have left in class, please use it to continue studying for the mini test tomorrow. Now, I know some of you might have questions and you have brought a lot. Please reach out to me through email or whatever it is you need to do. I'll do my best to respond in time. Okay? Sorry I have to leave, or I had to leave you hanging the day before. Anyways, but I have full confidence there's really no surprises for this mini test. Do your best and practice all the applications we've had. Now, projections. Projections is, long story short, it is a part of the dot product that you already know. Okay, so you could think of projections as literally the shadow portion or the component portion of vector A when you do A dot B. Okay, so when you do A dot B, you're looking at the horizontal component of vector A in the direction of B, right? And you multiply it with the magnitude of B. So you have A dot B, and that would equal A, the component of vector A in the direction of B, multiplied by the magnitude of B. The shadow, in other words, the projection of A onto B, is that part, right? Sometimes there are scenarios where all I'm interested in is that part. So this is the shadow or the projection of vector A onto B. So it's written like that. Okay. Notice how I am talking about the component, so I'm not interested in the direction. I'm only interested in how large the shadow is, excuse me, and in other words, how large is the projection, the magnitude. Okay. In the same breath, just know I could do the other way. The projection of B onto A. Let's pretend here the sun was up here, so it's blaring down, so my shadow is directly underneath. If the sun happened to be here and it's blazing downwards, the shadow will be right here. Okay, so projection of B onto A, the proj of B onto A, the magnitude, would be the magnitude of B cosine theta. Okay? Now you might be wondering, where does that come from? Get it to in just a second. It's literally just cosine ratio of adjacent over hypotenuse. Let's continue on. Let me erase this sun. It's sort of distracting. Here we go. Okay, so projections. The projection vector and its magnitude is typically denoted by this symbol, as I showed you. The vector that is written in a large way is the vector I am interested in, that's casting the shadow, and the little vector written just underneath as a subscript of the projection is the direction the previous vector is casting the shadow on. Okay? Now, the magnitude, aka the size of the shadow, aka the projection, the scalar projection of A onto B, is just the magnitude of that vector times cosine theta. Why? Well, think about this. Take a look at that triangle. Cosine of theta is equal to adjacent over hypotenuse. It's adjacent over hypotenuse. But we know that this adjacent can be written as, again, the shadow of A onto B. And hypotenuse is essentially the magnitude of vector A. So we have cosine theta equals the shadow divided by the magnitude of vector A. If I were to rearrange it to get the projection of vector A onto B, it would be the magnitude of A multiplied to both sides. That would be magnitude of A cosine theta. There it is. That's all. It's literally looking for the adjacent side, and that's equal to the hypotenuse multiplied by cosine theta. That's it. But as simple as it is, the applications of it and how I can word it, it could sort of twist things on you just because I'm asking for it in different terminology, vocabulary, and English. And so let's get some practice then. Okay, please also note that the magnitude, in other words, the scalar projection, maybe I should just leave that. The projection of A onto B can also be written as S projection of A onto B. In other words, a scalar projection of A onto B. But typically they write it with a absolute value on it. So, three cases. We could have an angle smaller than 90 degrees. We could have an angle larger than 90 degrees. Or we could have an angle at 90 degrees. Now this is easy. If the angle is 90 degrees, there's absolutely zero shadow being casted. So the projection is always going to equal 0, right? Which also makes sense because if I have vector A, cosine of 90 degrees, cosine of 90 degrees always equals 0. Easy, right? If the angle is under 90 degrees, absolute value of A, magnitude of A times cosine theta is going to give you some positive value. If the angle is larger than 90 degrees, cosine theta will give you a negative value. So the formula has a negative stuck to it, so a negative times a negative becomes a positive. Now, I don't want everyone to memorize this as a formula. I'm pretty sure you can use your common sense or you can use CAST rule. Projection is a magnitude. It's an absolute value, and I'm not interested in whether something is positive or negative. When you have an angle for cosine and it becomes a negative value, just know that it's supposed to be a absolute. So if it's the value that you get is a negative, just turn it back into a positive. Okay? And you'll see here. Example 1. Given two vectors of magnitude A equals 10 and B equals 16, angle between is 120, find the scalar projection of, so magnitude projection of A onto B is equal to the magnitude of A cosine theta, which is 10 cosine 120. Cosine of 120 happens to be a negative 0.5. So the answer is negative 5. But you know that it's an absolute value. So either you turn that into a positive, or you just remember that the formula has a negative in front of it, so you have a positive 5. Same thing here. The projection, the scalar projection of B onto A is the magnitude of B cosine 120, which is 16 cosine 120, which is going to be a negative 8. But because it's a magnitude and you know the angle is larger than 90 degrees, remember that there is a negative there, the value should be a positive. There you go. And so that's how we sort of go around it. Sure, we could have more complicated questions and there will be some heading your way. But just know, here are some connections that we can make algebraically. You know that this is the definition of dot product. So to go from dot product and only discuss the projection, that part, we can divide both sides by the magnitude of B, giving me the projection, the scalar projection of vector A onto B is equal to A dot B divided by the magnitude of B. Okay, it's pretty cool stuff. So long story short, you can, you know that you can do dot product in a different way. And if you have Cartesian vectors, then you can find the magnitude as well. You're going to see some interesting ways you can swap back and forth between an algebraic or Cartesian calculation with dot product and geometrically with an angle. All right. So here is the formula for a projection. That's the dot product divided by the magnitude of B. Please note, the magnitude that you're dividing is not the angle you are casting a shadow with. The magnitude you are dividing is the direction the shadow is being cast on. You just be very careful of that. Order does matter. The answer will be different if you do magnitude of A down here. Okay. All right. So the video, I know it's going to be uploaded so you can watch it at home as many times as you want. I'm going to just quickly move forward. If you can have a scalar projection, you better believe we can also have a vector projection. And it's the exact same thing, notice. Scalars, instead of scalar, we have a vector, so V projection, or you can just write it as just the projection of A onto B, like that. Notice this is the scalar portion. And all I need to do is multiply something to it. So what is that something? Well, please recall, a vector projection is the same scalar projection, the shadow, but now I am also interested in the shadow being cast in the same direction as B. But if I talk about the direction as B, I don't want to deal with the magnitude. So what's a smart way, or more of a clever way, that we can keep the magnitude of this component, the shadow, and stick the direction of B on there, but not have to worry about the magnitude? We'll change the magnitude of B into 1. In other words, the vector projection is the scalar projection of A multiplied by the unit vector in the direction of B. And recall, this is the way we calculate the unit vector. It is the vector B divided by the magnitude. So it's basically, magnitude with direction divided by just the magnitude. So the magnitude divided by magnitude becomes 1, and all I have is a direction left. So do the scalar projection and then multiply by the unit vector of the vector the shadow is cast on. Okay. And that's it. So it's also interesting, remember, by definition, the scalar projection was, look up here, A dot B over magnitude of B. So that means the vector projection of A on vector B is equal to the scalar projection of A onto B multiplied by this as my direction. Okay, so this is not dot product, it's not cross product. Here is the magnitude and here's the direction. So you could technically, because this is a scalar value and that's a scalar value, we could say here is my scalar value and the direction is going, that scalar value, this constant k or whatever, is going to be multiplied by vector b. Okay, so there's a couple of ways textbooks might present it, especially in university if you're taking courses like this. But for now, I think this is more than sufficient, this thing in the green. Okay. So let's try a practice question. Determine the projection of A on B. And they give you Cartesians. Interesting. They don't give you angles at all. That gives you a huge hint. I'm not dealing with this. I may have to be dealing with in the form of the scalar projection of A onto B multiplied by B, like that. Okay, I think I'm gonna have to use this because they don't give you an angle and I don't want to calculate the angle. Here we go. Determine the projection of A on B is equal to A dot B over the magnitude of B multiplied by vector B divided by the magnitude of B. So I'm going to have to calculate A dot B. I'm going to have to calculate magnitude of B. A dot B is 6 times negative 3 plus negative 8 times 4. I hope you remember this from previous class. That's a negative 18 plus a negative 32. This is a negative 50. Wow. Next, what is the magnitude of b? That will be, oh, well, that's a Pythagorean triple. Negative 3 squared, 4 squared equals 25. Magnitude of b is 5. So let's do it. We have negative 50 over 5 multiplied by vector b over 5. So how about I just do 25. Negative 2 times vector b. So that's negative 2 as a scalar number multiplying to the vector. The projection, the vector projection of a onto b is going to be 6, negative 8. Done. Cool. Exercise 3. Determine the magnitude, aka scalar projection of v onto u, if the magnitude of v is 16, the magnitude of u is 23, the angle between them is 29. Well, that's simple enough. We have the projection of v onto u means I am interested in the magnitude of v times the cosine theta. That would be 16 cosine 29, and that's it. Now let's take a look at what that answer is. 16 times cosine 29. 13.99, approximately 14 units, whatever that might be. Okay, so let's quickly recap. Projection is, in short, the shadow or the component portion of one vector onto another vector. That can be a simplified form or a modified form of the dot product. So that would be, here in this case, if it's a onto b, the magnitude of a cosine theta. But remember that projection is also a part of the dot product. And so we can have a slightly more complicated formula for it. Why? Because we're allowed to solve this and use this and solve for the unknown angle if I have two Cartesian vectors and we can do dot products with it. Okay, so we have a scalar formula, we have a vector projection formula, and both of these, in my head, they're one and the same. It's just a little extra little piece. But for you, it might take a little bit of time before you adjust and you can easily identify which one of these two is necessary. Okay, and that's it. Please use the rest of class to continue working hard on the mini test topics, specifically 7.1, Cartesian vectors, which means if you can do 7.2 and 3, you're pretty good for 7.1. Be comfortable with algebraic, that is unit vectors I and j. Yeah, and I think you can walk out of that mini test tomorrow confidently. Do your best. Contact me through email if you have any questions. I'll do my best to respond at a timely manner, and see you tomorrow.